Welcome to this video that will discuss the large middle chunk of this homework notebook for the fourth module. Here we will begin by setting the stage with a brief discussion on the role that roots play in optimization problems. Root problems naturally arise in optimization of smooth phenomena. Before we discuss how this happens, we address some terminology. What does smooth mean? For the purposes of this discussion, it means that the function has as many derivatives as we require. What is a derivative? It is a concept from calculus. We've certainly talked about this in the third computational module in the Part C lecture notebook, but if you've forgotten, you might want to go review that. Here you can just think of it in very physical terms. The derivative of a position as a function of time is velocity, the derivative of velocity as a function of time is acceleration, and so on. Is there a physically meaningful derivative of acceleration? Yes, it is actually called the jerk. And I do not mean it in the context of this lying jerk said we didn't need to know calculus. I would be the lying jerk in this case. Here are some motivating examples. Suppose a function, h of t, describes the height of a launched projectile, for instance a ball, a missile, or a satellite, and we wish to know the times t over some range of times from t0 to tf when the projectile reaches its maximum and minimum heights. Let f of t denote the first derivative of h of t. Then the solutions to f of t equals 0, meaning the roots of f of t, meaning the roots of the derivative of h, give the potential times of maximum and minimum heights. We can then evaluate the function h at all the roots of f to determine what the heights are at these so-called critical values. Suppose a function I of t describes the number of infected people infected with some virus at a given time t. Knowing when the infected number, let's say, spikes, meaning it produces a value that is maximum relative to other nearby values in time, is useful for guiding public healthy policy. Let's call that health policy. I'll fix my typo there so you'll have it fixed when I give it to you. And direction of resources. Like the example above, this requires knowing when the derivative of I of t is 0. Now, do we need derivatives and know how to calculate them by hand, or really how to do it with calculus is what I mean? The answer is no. We can use estimates of derivatives instead. You may recall that we developed the Python module differences.py in our third content module for the course. We will use that instead. So now problem 2. Let's minimize your cost to maximize your profits. All the code in this problem is done for you. You are prompted to provide some code comments, doc tests, and interpretations in markdown cells throughout. It is very important for you to read all of the instructions carefully. There is a lot of narrative to this problem. So the basic idea in this problem is that let's tell a story. Let's suppose you just discovered that you are the world's best pasta sauce maker. You should profit on this discovery. People love your sauce so much that they want to buy it a liter at a time. A liter is 1,000 cubic centimeters. That's a lot of sauce, and you can almost taste those profits. There is only one problem. You need to find liter-sized glass containers for your sauce. You talk with your co-packer, and they cannot find a distributor of glass containers that make the quality and quantity of liter-sized containers that you need. But your co-packer has a suggestion. We can just design and make our own containers. What a great idea. Your objective now is clear. Design a liter-sized glass container that minimizes the cost of production and thus maximizes your profits. However, there are some constraints. This is a glass container. It cannot have edges or corners. That would be ridiculous. The shape required is a right circular cylinder. We will ignore the slight curvature that you always see near the bottom and top of the container for simplicity. This is what we often do in modeling. We will consider that we have a solid glass bottom, otherwise the sauce will not stay in the container if there's just a big hole at the bottom, and an open top, because otherwise, where will the sauce be poured into if we don't have an open top to it? So this means that you have to determine the radius r of the circular base and the height h of the container. Assume that the thickness of the glass is the same for all shapes of containers so that the cost of the commercial grade raw materials used to make any glass container can be expressed in terms of the surface area of the cylinder. Your objective now is even clearer. Design a 1,000 cubic centimeter container with minimal surface area. The surface area of a container you specify with base radius r and height h is given by this formula, which follows just from simple geometry. Pi r squared is the area of the base of the right circular cylinder, and 2 pi r h is the surface area of the sides of your container. While the volume, and you add the two up to get the total surface area, which is a function that's just going to describe the cost of all the glass that's just going to be required to make it. The volume of a right circular cylinder is simply pi r squared times h, which is the area of the base times the height of the container. That gives the volume. Now, since the volume needs to be 1,000 cubic centimeters, this defines a constrained optimization problem, which is summarized mathematically as follows. Minimize the surface area, that is given by the formula pi r squared plus 2 pi r h, subject to the constraint that 1,000 is equal to pi r squared h. Now, you can use the constraint to solve for one of the variables in terms of the other. So h is equal to 1,000 divided by pi r squared. You just obtain that by dividing the 1,000 by pi r squared in your constraint formula. We can now substitute this into the surface area equation to simplify the problem to the following. Minimize the surface area as a function of radius, where it's simply given by pi r squared plus 2,000 divided by r. I've just substituted the 1,000 over pi r squared in for h in this formula, and you'll notice that if you do that, the 2 times 1,000 gives you the 2,000, the pi's cancel out, and the r divided by r squared leaves you with 2,000 over r. The only obvious constraint now is that r has to be greater than 0. The circular base has to have a positive radius. Otherwise, all positive values of r are now, let's say, fair game in what will be the optimal design of the container. Once r is determined, we can use the constraint h equals 1,000 divided by pi r squared to actually determine what the height is. Now, to 2 decimal places, assuming that our machines can only be set to a tolerance of 0.01 centimeters in the manufacturing process, the value of r that minimizes the surface area is 6.83 centimeters. So I'm giving you what the answer is in terms of the optimization. We use what we have learned in the Part A lecture notebook as well as the previous notebooks to approximate this answer. So this should be the value that is the root of the derivative. All right, what are you asked to do in problem 2a? You need to develop intuition about this problem. It is always good to build some intuition about a problem, and we do that here. The way we do that is by using visualizations of the data and the formulas involved in this problem. So you need to add a docstring, a doctest, and comments to the function surf area shown below, which is a function of r, and you need to explain what this function is. Make sure to demonstrate that your doctest passed. So you will need to create your own code cells after this in order to show that your doc test passed. But this code is effectively written for you. The only thing that's missing are comments. There's not too many lines of code here, and a doc string that explains what this function is, what r is, and some doc test. You can use this formula in this narrative, hopefully, to write a reasonable doc string doc test and some comments to explain what's going on. Now, you need to add code comments to all of the code cells below to explain what is going on and use markdown cells to contextualize the results. So here, R is set from 0 to 40, and I use 100 points. Now, notice I use some slicing, some index slicing, where I start at 1 here and then go to the end, and I start at 1 here. Then I plot the surface area for 1 to the end as well. So now if we plot this formula, here's what we see. We see the surface area of the 1 liter container versus the base radius is given here. So I'm saying the surface area is plotted on the y-axis, the radius is plotted on the x-axis, and look at this, the plot of the surface area. So as we vary the radius, we see that if the radius is very small, the surface area is actually incredibly large. And then there is a point around 6.83 where the surface area is minimized. And then when you increase the radius from there, the surface area again continues to increase substantially. So now I show you how to use the differences module to approximate the derivative and plot it on the same axes. So here I've imported differences as diff, so you need to make sure that that differences module is in the same directory, the same folder as this assignment, so that it can be imported. So now I create a figure of a certain size, and I'm going to use a twin set of axes to make two plots with two different scales on the same figure. So first in blue, I plot that surface area curve that we saw above, and then in red, what I plot is the derivative approximation. I use the center difference approximation to the derivative, and then from that derivative module, all I need to pass it is the function I'm approximating the derivative, an array of values for which I approximate the derivative, and this h parameter that controls how well I'm approximating the derivative. And that was something discussed in the lecture 3 part C notebook. So if I plot this, here we go. In blue and on the left y-axis, I'm showing the scale of the blue curve, which is the surface area. And then in red and on the right part of the figure, I'm showing the scale for the finite difference approximation of the derivative ds versus dr. So notice you don't need calculus. You don't need to know how to compute this derivative. You just need to know how to use this differences module, give it a function, the array of values where you want to approximate the derivative, and this step size parameter that determines how you approximate the derivative. That's all you need to know how to do to approximate the derivative. And I'm showing you how to do it. So now I've plotted with these dotted lines. I'm showing where the derivative crosses the zero axis because it's on this curve. Notice that dotted line is connected over here, so it's where that's 0. And I'm plotting a vertical line at 6.83 to show that's approximately where the derivative is equal to 0. That's all I'm doing here. So it's just a good number of plotting commands, but there's not too many, and I provided some comments here, but you should add more to all the code cells below, right? For this right here, it was just this code cell. You should add code comments to explain what's going on. You should also add code comments here. We are importing the differences module. You should add more code comments than I provided in this cell to explain what's going on. And then you should interpret all that was shown in those code cells above and this explanation of what's going on. I've said some of it in words, but it's good for you to write it down for yourself. Now, problem 2b. Approximate the optimal radius through brute force. Since r is greater than 0, we may be tempted to search for an optimal r value in, let's say, the interval 0 to 40 units in centimeters, because a 40 centimeter base radius seems rather large, so you would probably truncate it there. Now note that a value of, that should have been of, so I'll fix my typo right now and it'll be fixed for you. Note that a value of r equals 0 is meaningless, because then you're saying that the base radius is 0. There's no base. So that's why we consider values of r in the half open interval 0 to 40, because we don't allow the radius to be 0. Pay attention in the code cells below to see how we avoid using r equals 0, which is related to this slicing. We could do this in a brute force fashion as shown below that avoids any approximation of the derivative. You are asked to add comments to each of these various code cells, there's just a few of them here, and interpret the result in the markdown cell provided below. So notice first we will start with 100 approximate values of r from 0 to 40, and then we evaluate the surface area function at all the r values that we created that were greater than 0. And then we use the argmin function in NumPy to find the index where this function, where these values, this array of values, is minimized. And then we approximate what our search is. And notice we add 1 to what this index is. You should explain why we add 1 here, and it's based on this index slicing here. And notice we're using the around function, and we're rounding to 2 decimal places. So you can run that here, and you see 6.87 is what we approximately get when we evaluated at what is amounting to 99 points here because of how we sliced. If we used 1,000 points and repeated this process, we get 6.85. If we use 10,000 points, which means we evaluate the surface area at 9,999 because of our index slicing, and then we repeat, we finally get 6.83, which is what we know to be the answer because I've given that to you at the beginning of this problem. So you should interpret all of what's going on here. It doesn't, just a few sentences, a couple bullet points about the process and how many computational solves we required of our model, our surface area model, to get the answer to the tolerance we wanted. Now, the bracketing, now we use a bracketing approach. The brute force approach is not elegant, but it does get the job done. Can it always get the job done? Well, while this function S for our surface area is not expensive to compute, meaning it does not take a lot of time for the computer to evaluate the surface area, there are many functions in practice that are incredibly expensive to compute in terms of the amount of time and resources required to evaluate them. So for example, in my research and when I've reviewed papers for publication in certain reservoir engineering journals, there's the simulating of optimal net present value of a new project, which is something that is studied and researched, and it's critical in management decisions about whether a project is worth pursuing or not. They require simulations of subsurface flow that often involve complex partial differential equations discretized over large, and I mean complex in terms of the complexity, not necessarily complex valued, but very difficult to describe partial differential equations discretized over large physical domains that may require a supercomputer to solve. Subsequently, it may not be feasible to compute more than a few simulations. In other words, the brute force option shown above is not only inelegant, it is also impractical in many settings. Below, we implement a version of the algorithm for the bisection method from the 04 lecture part A notebook to approximate the R value that makes the centered difference approximation of ds dr equal to 0. And we use h equals 0.001 when calling this finite difference function. We use an interval of 1 to 40 and a tolerance for the radius and a tolerance for the interval length of 0.005 in the algorithm to ensure that the estimated optimal radius is within 0.01 centimeters of our achievable machine tolerance. The version of the bisection algorithm used here also outputs the actual number of iterations used to achieve the desired tolerance. Now, why am I not asking you to use the module you created in problem 1? You could do that. You'd have to modify it based on things I'm asking you to do here. But also, I want to be sensitive to if you've made mistakes in that module, I don't want it to impact your ability to get the right answers here. But you might want to create your own code cells and even update your module so that you can replicate what you're seeing in this part of the problem, part of this assignment notebook. So what you need to do is use the markdown cell provided below to comment on the number of times the surface area function S must be evaluated to achieve the desired tolerance in the algorithm, and you need to compare that to the brute force approach. So notice here, I use a lambda function where I'm using R as the input to the lambda function, and then this is how I approximate the derivative of the surface area function as a function of R with that step size h of 0.001. So now I can just evaluate this as a function of R, and it will call the center difference approximation to the surface area function with the value of R I've passed to it. So this is a very clean and slick way to use the differences operator to approximate derivatives. So let's run that. I'm not going to go over the compute bisection function here. I'm just going to show that it runs. I just kind of edited and moved this over from the lecture notebook. So we'll just go ahead and run that now. And now I'm going to run these code values here. And notice I'm saying what the number of iterations was to my approximation of the optimal radius, and notice 6.83, and that it's achieved in 13 iterations. What you need to think about and actually try to answer is, with 13 iterations, how many times was the function surface area actually computed? Because in the derivative approximation, this gets evaluated a certain number of times, and then it gets evaluated a certain number of times inside of here. So you have to figure out every time you approximate this derivative, how many times does that get evaluated? And then in this, how many times does the function f get evaluated within this interval, or excuse me, within this algorithm? if there's 13 iterations. If you figure those two things out, then you'll be able to say exactly how many times that S got evaluated and how does that compare to, let's say, 10,000. Then in part D, I'm asking you to do the secant method. So below we implement a version of the secant method for demonstration purposes. That was from the part A lecture notebook as well. And it also checks if the magnitude of the difference between successive estimates is below a tolerance to approximate the R that makes, again, the same centered difference approximation of DSDR equal to 0, which was defined in part C above using H equals 0.001. So to initialize this algorithm, we use initial guesses of 1 and 1.1, 5 and 5.1, 10 and 10.1, 20 and 20.1, and 30 and 30.1. We set a maximum number of iterations to 100, and we set the tolerance for successive estimates to be 0.005 again in order to make sure that we approximate the optimal radius within the achievable machine tolerance. We use the what you are asked to do is to use the markdown cell provided below to again comment on the number of times the surface area function must be evaluated to achieve the desired tolerance for each different set of initial guesses, and compare this again to the brute force and the bisection approaches that were shown above. So I will just run through the code, and I'm just again producing, this is this edited version of Secant Method for demo. And notice I have 6.8. If you were to round this would be 6.83. It took 11 iterations. 6.83 effectively, if I rounded it, would give me 5 iterations with 5 and 5.1 as my guesses instead of 1 and 1.1. Well, that makes sense that this should take less iterations to get to some value that's closer to where my initial guesses were than this. 1 and 1.1 are farther away from 6.83 than 5 and 5.1 are. And then if I use 10 and 11.1, well, it takes 6 iterations. And then 20 and 20.1 takes 11, and 30 and 30.1 takes 17. And now you need to do your comments and comparisons for this problem here. That is the end of problem 2. Now for problem 3, we realize we forgot the lid. How could we forget the lid? So yeah, we kind of forgot to account for the cost of the lid in the container. Oops. Suppose that the cost of the materials for making the glass part of the container is given as a fraction of a cent, 0.001 dollars per square centimeter. In other words, it costs 1/10 of 1 penny per square centimeter of glass needed. Suppose the cost of the materials for making an aluminum lid is twice as much. So it's $0.002 per square centimeter. So it costs 2/10 of 1 penny per square centimeter of aluminum needed. The total cost in US dollars to produce a single 1 liter container with a lid is now given by this function. So this is the surface area function, pi r squared plus 2000 over r. We're multiplying by what the cost of the materials for the glass is. And then we're having to multiply by the cost of the lid. So this cost function is now a function of r. This is produced in the function total cost below, which you need to add comments to, a docstring and a doctest, and again show that your doctest pass. So you need to redo the analysis, but it is a lot of copy and paste. So you need to use the code and markdown cells below and probably create a lot more of your own code cells to repeat the parts A through D of problem 2, where you just use total cost instead of the surf area function. Then I want you to compare the optimal dimensions for both R and H for this problem and problem 2. I said problem 1. It's problem 2. Let me write that. There we go. And problem 2. Now, we've only computed R so far. I haven't shown you what H is above. You need to use this R value to compute what H is, and the R value that you'll get from this cost function that you optimize to figure out what H is. Now, if you do a quick online search, that will reveal that a typical 24-ounce pasta jar, which is equivalent to about 0.7 liters, has a height of about 6.61 inches. That would be H, with a base diameter of about 3.37 inches. Now, a diameter is just 2 times the radius, so you can divide this by 2 to get the radius. Which of these problems have we solved? involving minimizing the total cost based on this function versus minimizing the surface area produce results that look more like a typical pasta jar in terms of the ratio of height to diameter. This is something you need to answer below, and you should really think about what that implies and how people come up with the sizes of these jars. These aren't just arbitrary choices, they are minimizing cost. So now, problem 4 goes back to exploring built-in optimization routines in SciPy. So this is kind of removing a little bit from our functions, but we'll use our surface area and total cost functions as tests for these, as examples. So the SciPy library does have an optimization sublibrary that you can import and play with, and I think you should know about it, so that's why I have a problem for it. A thorough tutorial is given here, so you can click on this and find it. You can turn a lot of examples from that tutorial into your own Jupyter notebook. But the best initial reference may just be this documentation. So I suggest that you spend 20 to 30 minutes looking through these links and starting to play around with it on your own. And below, I get you started on a useful function in this sublibrary, this optimization sublibrary. You should read up on the documentation for this function. It is the minimize function. I want you to play around, see if you can figure out how to choose which algorithm to use, and how you can force this or other built-in optimization functions to use certain algorithms. Basically, this minimize function is like a wrapper function around other algorithms, much like how you built a wrapper function for your optimization module, for your root finding module, excuse me. This is a rather open-ended problem. I want you to comment, experiment, and explore. How deep you get into it is up to you, but you need to explore at least 3 different functions / routines, whatever you want to call them, within this sublibrary. I'm showing you the minimize. You should please do at least 3 more different ones than minimize. You should apply these routines to either surface area, total cost, or their derivative approximations as appropriate. And you should discuss your results in a markdown cell. So that is what this problem is asking you to do. It's a little open-ended. I want you to explore on your own the optimize sublibrary and just play around. Learn what the options are available to you, and then write about them in a markdown cell. So that will be it for this video. I will make one more video for this notebook, for this assignment, and it will be involving some important concepts that involve differentiating functions defined in terms of integrals.